Okay, hi everyone. Today we're working on the lesson length of a curve. So I'm going to give you guys a simple drawing and we're going to see what is the length of that line. Now let's do something kind of easy. If I give you guys a problem that looks like this, let's do 1, 2, 3, call that 1, move over, let's do 3 over. So y is equal to 2 over 3, rise over run, right? Rise 2, run 3. X plus 1. That's my equation. And they ask you, find the length of y between 0 and 3. Oops, not t. Between x between 0. Oh, wrong way, I'm sorry. 0 and 3. Okay. So we're going to find out what the length of this line here is. Okay. Now careful, some people might say take the integral, but integral is area underneath the curve. That doesn't work for me. We could, get a ruler, right? I can get a ruler here and try measuring this, right? What's the length of that? But do you guys remember in Algebra 1 how to find the distance between 2 points? And you might remember, you might not, because it's one of these funny equations. And the distance between 2 points is really the Pythagorean Theorem. It's a squared plus b squared equals to c squared. You guys remember that? If I draw a triangle here, it's the Pythagorean Theorem. In this case, it's going to be 2, 3. So what's the third side? Well, 2 squared plus 3 squared equals to c squared. 4 plus 9 equals to c squared. C is equal to the square root of 13. So it's square root of 13. So it's 3 point something. Okay. But then in algebra, you learned a different method for this, and this was the square root of, you subtract your x2 minus x1 squared plus y2 minus y1 squared. You guys remember this? That was the distance formula of 2 different points.
Why would
And
we use that when the other one is simpler?
it is. And the thing is the way we talked about in Algebra 1, it's really just this equation here, where we subtract our y's and our x's, and that tells you, so let me give you this example. If I say this is our, actually no, I should have spun these around, but whatever. This point is 3 comma 3, and this point is 0 comma 1. And we say, what's your y? Well, isn't your y 3 minus 1? What's your x? That's 3 minus 0. That's your x. And this was our distance equation, which is really just the Pythagorean Theorem, given 2 points. So that's 9 plus 4 square root is back to square root of 13, like we said before. Now, to think of this in a calculus sense, this is a distance, some type of let me write this a little nicer. This equation from algebra, to find the distance between any 2 points, you find a little bit of the x. So instead of writing x2 minus x1, we'll just call this we'll call it delta x. Delta x. Okay? And then our distance between y2 and y1 is some delta y, right? Some change in y, some small change in y. And we take the square root of that. And that's our distance formula. Oops, sorry. I just wrote dx naturally. That's our distance formula. Now, this works really nicely for straight lines. But what about a curved line? Now, if I give you a function now that looks more curved, let's say, let's pick something like this. Okay? And I want you to find the length of, let's take it from here to here. We'll call this 2, make this up, and call this f of x. Okay. Well, how do I find the length of the curve? Because if I use my traditional line, that would just give me a straight line. And that's not what we want. So let's look at it a little differently. In calculus though, haven't we talked about limits as we approach zero, making small little cuts instead of big cuts? And what you could do is you can draw little tiny cuts instead, little tiny lines here. And the smaller the lines, the more accurate your length is. So for instance, you would pick points 1 and 2, and then 2 and 3, and 3 and 4, and 4 and 5, and 5 and 6, and find the difference between all those lines and add them together. But of course, that would still be an estimate. So you find even more dots in between. So what happens is we make our differences even smaller. And the idea is, remember I had this idea limit as x approaches 0? So we want the difference between these 2 points to become even smaller, right? And this leads to even a smaller distance between the two. So what we were talking about here is the big idea. We're adding up all the differences between our x values, and I'll use a k here, square it. If I put a square here, right? That's our distance formula, plus the differences in our y values, okay, on the same count, squared. So this is the rough idea. Okay, the rough idea is finding a distance between a straight line is pretty easy, Pythagorean theorem. But to find a curved one, that's not a straight line, right? Pythagorean theorem doesn't work anymore. We'd be screwed. So what we do is instead we draw a trillion, billion, cajillion little Pythagorean theorems and find each of those distances and sum them all up and add them all up. And that will give us our full length. So that is the basic idea here. Now, how can we do this? Well, that's where calculus comes into effect. Where, remember, integrals add everything up. So instead of using a sigma sign, we're going to use an integral sign. And let's go ahead and try to figure out the rest of this part up. Now, if you take a look here, to take an integral, I'm going to change these up a little bit. I'm going to call this, instead of delta x, I'm going to call this dx for a little bit of x, plus a little bit of y here for dy. How are you guys feeling about that? Now, this formula here kind of gets us in the mood for an integral, but we're missing some stuff. So first thing I want to do is take a look here. If we have a dx squared and dy squared, and then even if I throw an integral in here, what are we still missing? We're still missing the dx or dy at the end, right? I'm pretty sure you guys wouldn't have thought about that. But here is the gimmick, and here is the trick. I'm going to erase this one more time. And here is the trick. Well, I'm going to trick the problem. I'm going to rewrite this instead. I'm going to say instead, I'm going to divide everyone by, you know what? I'm going to actually, yes, I'm going to multiply this problem. Here, okay, take a look here. Here's a big expanse. Integral square root dx squared over dx squared plus dy squared over dx squared, and I'm going to multiply dx squared on the outside. And this, oh sorry, no, not dx squared, just dx on the outside. This is the trick. Okay? This is the gimmick. I needed a dx, so I gave myself a dx. But here are the steps of me getting there. Okay, so now you guys can kind of see the process here. I'm going to show you guys how we got there. So here's what we did. We start off with dx squared plus dy squared, and I gave myself a dx. But can I just write dx in a problem? You cannot. You have to balance out the equation. So I'm going to write dx over dx. How do you guys feel about that? That's fair, right? Me just writing dx over dx is just 1. Right? That's a trick that we can use. And then what happens is, what if I want rewriting this as dx squared plus dy squared? I'm going to write this so you guys can see it. 1 over dx times dx, right? Separating it. Now on the side, let me give you a question. If I write 3 square root of 2, and I want the 3 to go in, isn't it the same as 3 squared times 2? Okay, So you can write something into a square root by squaring it. And that's what we're going to do. We're going to push this into the square root by squaring it. So it's square root of dx squared plus dy squared times 1 over dx squared. Dx. You guys feeling this? See how I did that? It looks complicated. Like, why would you ever do that? How could you ever come up with something like that? But first, if we want to change this summation to an integral, we need to find that dx from someplace. So fine, I'll give myself a dx. Here's my dx, but the way we did it is we cheated. We said dx over dx, and we pushed our 1 over dx into the problem. I'm going to distribute this. Dx squared over dx squared plus dy squared over dx squared. Okay. As we mentioned before, what's dx over dx? That's going to be 1. This leaves us with the integral, the square root of 1 plus, and we write it as dy over dx squared dx. Now, have we seen what dy over dx is? Dy over dx is another fancy way of saying y prime. So what happened was we took the distance formula from algebra 1. We said we could find the length of this curved problem. Sure, if you add up like
the dx not squared on the bottom?
I took the square out as a parentheses.
Oh, okay.
Okay, so I said parentheses squared. Okay. Now, so back up here, let's go back to how we started. We started to say, hey, you know what? I can find the distance of a line. That's easy. Okay, that's just distance formula. But of a curved line, man, that's not straight anymore. So we cheat. We take small lines instead. And the more lines we take, the better our accurate, the more accurate our estimation. Now, what if I take an infinitely many set of these? What if I say do this to infinity times? All right, sure, then it'll be super accurate. The lines will be so small, it's like a dot. And then we said, well, okay, a summation is the idea of an integral. Fine, let's change it to integral. But when I do that, I need this dx. So we cheated by giving myself a dx and throwing the dx into the problem by squaring it. We see a trick here. Dx squared over dx squared cancels out to be a nice, easy 1. And dy over dx turned out to be, hey, that's just another way of saying the derivative. So here's what we come up with. To find the length of a curve, it's just take the derivative of the equation and follow this simple new version of the distance formula. Okay. So here's my proof for you. This is my distance formula of a curve, of any curved surface. Now let's go back to our original problem. We said our original problem was y is equal to, what did we say, 2 over 3? Positive 2 over, or is it? Positive 2 over 3x plus 1. 2 over 3x plus 1. If I want to find the curve, so the length of this curve from 0 to 3, we can use this formula and we'll call this a to b. Up here, a to b. Okay. So here we go. We're going to plug it in. The integral from a to b from 0 to 3 of what's my distance formula? The distance formula is the square root of 1 plus, okay, we have to find what dy over dx is. So the derivative of dy over dx is simply 2 over 3. You guys feel okay about that? 2 over 3. We're going to square it. Careful, we have to square it. And dx. For this problem, we can use a calculator, but it's pretty constant. So it's 1 plus 4 over 9. That's 9 over 9. That common denominator plus 4 over 9 is 13 over 9. That's a constant. So we have 13 over 9, square root of 13 over 9, integral between 0 and 3. I can take the square root of this. It's, did I mess up anywhere? Just making sure I didn't mess up anywhere. Oh yeah, okay. Dx. The integral of this is, I'm going to write square root of 13 over 3 x, plug in 0 and 3. Bring down the 3. Square root of 13 over 3 times 3 minus square root of 13 over 3 times 0. And our answer is square root of 13. Oh my gosh, it worked. Yay! For a stupid line. And for a stupid line, why didn't you, Mr. Ko, just do the distance formula? Cry. Why would you do that to us, Mr. Ko? But it worked. Now, let's do another problem. If I give you the problem is y is equal to x squared, and I want you to find the length
How
of...
did you find the dy over dx?
Oh, what is another idea of dy over dx? It's just the derivative. It's just y prime.
Oh, okay, okay.
So what we're doing is we are switching this problem. Instead of making it a y problem, we're looking at the slopes of this problem. Because according to our identity here, all this work here, dy over dx is what we needed to find the area, the cumulative change. All right, so let's use this example here, and we're going to blow it up into x squared. Now, we all know what x squared graph looks like. That's what it looks like. And we're going to find between, what is the length of the curve between 0 and 2. Okay, so this is the formula you need to remember. The distance formula for us, the length of a curve, is between a and b, the square root of 1 plus dy over dx, or you can just say y prime squared dx. It's very similar to our Pythagorean theorem. Okay. So let's just set up y prime is 2x, our a is 0, our b is 2. Okay, all right, so here we go. D is equal to the integral from 0 to 2 square root. Now don't overthink it. It's just really 1 plus, we don't write x squared, we write the derivative of x squared, which is 2x squared dx. Do not forget that squared, it will mess you up. Okay, now we're going to use our calculator because for me to take the integral of this, I would hate my life. Okay, so now we're going to use our calculator. So you go ahead and hit math 9 on your calculator. You're going to use the, and plug that into the calculator, please. All right, so let's go ahead and plug this into my calculator. Oops, not that one. We have math 9 from 0 to 2. A square root, second square root, 1 plus. Make sure that's a plus, is not a minus. I made mistakes like that before. 2x squared, and then make sure you write dx. All right. I got the answer 4.646. Okay, we got 4.646. And that's our length. Easy peasy. Seemingly, right? Seemingly that's easy peasy. Okay. So, what else can we do here? All right, let's try another problem. What if I wrote y is equal to x cubed? Right, y is equal to x cubed from negative 1 2, 1. X cubed graph looks like this. 1, 2, 1. Negative 1 to 1. Right. What is the distance from negative 1 to 1 anyways? If I just drew a line here, what would that length be? This is a 2 by 2. So if you look at a box, 2 by 2, right? That's 2 squared of 2, just FYI. And 2 squared of 2 is something like the square root of 8 is about 2.8. So this length is about 2.82. So if I follow the curve should be longer than 2.82, right? Just saying. All right. So how would I find the length of this curve? Well, just to set it up, d is equal to the integral from negative 1 to 1, the 1 plus the square root of 1 plus. We don't put x cubed. We're not looking for x cubed. We plug in the derivative. So y prime is equal to 3x squared. 3x squared dx. Whatever number you end up with, that is our length. That's it. Okay.
Mr. Code, don't we have to square?
Oh, sorry. Thank you. Darn it. See, I told you I forget it, and I always forget it. That's not a joke. I was working on problems yesterday, and I was like, oh my gosh, I kept getting it wrong because I forgot to square it. And then for some reason, I put a minus sign there. Oh my goodness. Okay. Now, here are some caveats about us using this. Okay, there's some problems with us. Okay. One is that, of course, it has to be continuous, right? Hey, if it went from here, jumped, and then took off again, this isn't going to work. Okay. So if it's not continuous, it's not going to work. But also here is the next part. The derivative has to also exist. Okay? The derivative has to also be continuous and exist. Okay? The derivative has to be continuous and exist. Okay? So our problem is that not every problem is going to work. And one that the book throws out is this problem here. Y is equal to x to the 1/3 power. Okay. Now, if I rewrite this problem, if we look at the problem, what it is, the problem looks like this. Okay. And the problem's going to say, this is what the book's example is, and it's a pretty good example for us to talk about. Okay, so we want to go from negative 8, negative 2 to over here 8, 2. I put a link in the homework for the book if you guys need to look it up, and this is in 8.4. Now, if we go and take the derivative of this problem, okay, let's go take the derivative. And the example is, if I ask you to find the length of y from negative 8 to 8, okay? Negative 8 to 8. I'm looking for the length of y from negative 8 to 8 of the graph. So we're looking for what is the length from here, following it all the way up here. It's a curved surface, so we're thinking, man, this is going to be super easy. Let's take the integral. All right, let's just set it up. So if I set up d, and this is going to fail, okay? Future, this is going to be a fail, okay? FYI, this is going to be a fail. FYI, I want everyone to know this is not going to work. So we take our distance and we say, you know what? Let's just plug in negative 8 to 8, and we're going to say square root of 1 plus the derivative squared dx. Okay, seems like an easy problem. But I want you guys to notice something. Let's go and take the derivative of y prime. Y prime is equal to 1 over 3 x to the negative 2/3. Rewriting this as y prime is 1 over 3, and we're going to say it's going to be the cube root of x squared. Now, does this derivative exist between negative 8 and 8? Does this derivative exist between negative 8 and 8? And this is like a pre-calc skill. And what value does it not work at? when we divide rationals, or when we're working with rational functions, this does not work when x is 0. What happens when we plug in 0? Doesn't it shoot off to infinity? What are we supposed to do with the derivative at infinity? Imagine if I just stuck infinity here. Game over. You're done. Doesn't work. So you have to be aware of it. Whenever I'm looking at a problem and I take the derivative and that derivative doesn't exist someplace, we cannot use this method. It's a fail. But does it mean we're dead in the water? Turns out, what if I rewrite the problem instead? Okay. What if I rewrite the problem and I say, you know what? Instead of looking at y is equal to, let's make it x is equal to. Instead, because this was a fail, right? See, this died here, fail. And if I plugged it in, we ended up with infinity and we're screwed. Doesn't work. Instead, rewrite the problem. And we rewrite the problem and we're going to say instead y is equal to x to the 1/3 power. If I cube both sides, we have x is equal to y cubed. And this is the exact same problem, but in the different direction. We're going to switch directions. Instead of going the x direction, we're going the y direction. And we can do the same exact problem, but in the y direction. So let's go ahead and take the derivative of this. This would be x prime is 3y squared. Okay, that's not hard, right? This could be considered dx over dy. Okay, looking at it a different way. Now, if I spin my problem now, we can do the integral from a to b, but these are, careful, I need to put a little note here. These are y's now, y values, because we're spinning the direction around. So instead of using x values, we use y values. We do the same distance formula, 1 plus, instead of saying dx over dy over dx, we're going to say dx over dy. We're going to square it, and instead of saying dx, we say dy. So please take a couple of notes here. Because we spun it around, we changed some parts about this equation. Let me go ahead and show you the original one, okay? The OG. The OG one in x, okay? In x is integral from a to b, squared of 1 plus dy over dx squared dx. So this looks almost exactly the same, except I'm switching our x's for our y's. Now let me ask you about this derivative here. Are there any values that don't work for 3y squared? Well, let's look at our y's. Our y's are between, take a look up here, remember our y values are -2 and 2. -2 and 2. So is this derivative, does it exist between -2 and 2? Yes, all values work there. So we took a problem that actually didn't work because the derivative would have given us infinity. It would be undefined there. And we spun it around and we rewrote the problem in terms of x instead. Now we can set up the problem. So go ahead, let's go ahead and set up the problem. So we're looking at the distance is the integral from -2 to 2. Take a look here. These are y values. Okay, these are y values.
Mr. When's the biggest hint that a problem won't work?
Is when you look at the derivative and when you take the derivative, it's going to be a fraction. See, this derivative is a fraction. And you're like, oh man, I'm going to have a 0 someplace. Now, if that 0 on the bottom doesn't fall within your range, you're still good to go. Right? But 0 here is between -8 and 8, so we're screwed. If I gave you the problem and instead told you, let's say from 1 to 8, hey, we're good to go. This totally would have worked. Because we avoided the 0, but we didn't avoid it. So that's why we have to spin it. But the problem is not that much different, except I just changed my variable. And we're saying 3y squared, squared, and then dy now. Everything else is plugged into your calculator. If you guys want to plug in your calculator, the book says the answer is approximately 17.26. This seems like somewhat of a Like, you really have to think about it. And it's true, everything in math, there's a reason why you do it. There's a reason why we choose a method versus another method. And the cool thing about calculus is that hopefully it makes sense. Like, there's a reason why we couldn't do it. We can't use our original formula because we would divide by 0, because 0 is between -8 and 8. Darn, that would give an answer. Yes, go ahead.
So for the when you flip it, all you have to do is make x be alone, right? And then put everything on the y.
Yes.
Okay.
Right.
Okay.
We solve it for x now.
Okay. Thank you.
Now. Yeah. Okay. Now, here's another problem. Let's look at it. So we've looked at a lot of different types of integral problems, and here is another problem. Imagine if I told you x was equal to the integral. No, so that's not x. Y was equal to, sorry about that, the integral from, let's say, 3 to x of sine of 2x dx. Oh, sorry. I need to change the variable. I always mess up and I always write the same variable. T. Let's use t here. Okay. Your equation, your curve is actually an integral problem. Your curve is actually an integral problem. All right? And then I'm going to say to find the distance between 0 and, let's say, not 0, darn it. Let's say pi and 2 pi. Okay, x is between 0 and, so pi and 2 pi. Now this problem might look a little confusing with this integral sign, but let's go ahead and set up the problem like we typically would. To find the length, the distance, or sometimes use the letter L, isn't that the equation integral a to b, the square root of 1 plus dy over dx squared dx, okay? Okay, that's the equation for my distance formula, my length of a curve. Now, how do I get from here to here? Don't we just take the derivative? Okay, everyone has to be clear on that. What we do for this problem is we always take the derivative to plug it in to find the length. Okay, take the derivative. Have we taken the derivative of integrals before? What should the derivative of an integral essentially do? Shouldn't they cancel each other out? And that's what I want to make a point of. Y prime is the derivative of this integral. And what do we do with derivatives of integrals? Hopefully you guys remember what this is. We just plug it in. And if you want, you remember the chain rule. In this case, there's no chain rule here. This problem is easier than any of the other problems because the derivative integral gives us everything we need, from pi to 2 pi, 1 plus sine 2x squared dx. This is applying what we've learned before. And again, calculus problems can get super difficult because they give you crap like this, and you're like, what the hell am I supposed to do with that? I don't know how to deal with integrals. Do you want me to take the integral? But the point is that when I take the derivative, the integral was going to cancel out anyways. You just have to remember what to do with the derivative of an integral. The chain rule, if you want, is followed by the derivative of x is just 1, if you want to. Just to remind yourself about that. Okay. Another issue is that what if we have absolute values in the problem? What if we have absolute values? And here is a thing about absolute values, is that whenever you do have absolute value, you have to split it. So just be aware that it's hard for us to take, we don't take integrals of absolute values. So this is, I guess, a side note. Integrals of absolute values. You can do this on your calculator, but if you're trying to do this by hand, it could mess you up. So example is if I write the integral of, let's say, -2 to 2 of, let me think, I'm trying to write this. Okay, if y is equal to absolute value of x, okay, of y and then dx. Okay. So looking at the problem, this looks like that. Sure, and if you plug this in on calculator, that would totally work. But how do we do this by hand? Is that if I write this -2 to 2, okay? Now, have we learned any rules about taking the integral of the absolute value? And the idea is that now we're stuck. So instead, what we do is we talk about this function y. Y is a set of equations of x. Okay? When x is less than 0, if I plug in numbers less than 0, aren't those going to be negative? And what we do is we put a negative in front to force it to be positive. Force to be positive. We do this manually. And when x is greater than 0, does it matter? No. 0, right? So we break up this equation into the integral from -2 to 0. You end up with what equation? Take a look here. You end up with a negative x equation. On the right, the integral between 0 and 2, we use our regular dx equation because it doesn't matter. Okay. So to be clear, whenever you do take the integral of an absolute value problem, we can't do this. There's no rule for us to do this. So what we do is we break it apart and say, hey, when does the x have a problem? When does it flip the sign? And we create two different problems based on that. Okay. When x is less than, see how this is less than 0, we have to use our negative x. When x is greater than, we use our x problem. And if you plug this in your calculator, both of these will give you the same answer. Okay. All right. So why is this a problem for us? Is because also here is the case when it comes to the derivative. What is the derivative of, what's the derivative of the absolute value of x? Do we learn any rules about the derivative of absolute values?
Isn't it ln?
No. That's the integral. The integral of 1 over x dx is ln of absolute value of x. Right? Okay. So here is where we're stuck. If I give you this graph here, and this is what the graph says, right? Well, is the derivative over here is 1 and derivative here is -1, how are we going to get our derivatives to change along the way? And this is what you do. Is what we did just previously in this problem. We say, hey, y is absolute value of x, right? But this is also a piecewise function where it's x sometimes. When x is less than 0, don't we have to throw a negative in front to make it positive? And x is greater than 0, then we can leave it as a positive. So take a look. I made a piecewise function here that represents an absolute value. If I plug in -1, hey, isn't negative become a positive 1? I pretended there's an absolute value there. And this is what we have to worry about. Now, take the derivative of this problem. The derivative of negative x is -1 when x is less than 0, which makes sense on the graph. And I always hate drawing the J-Lenos. Is positive 1 when x is greater than 0. Okay, so this idea, whenever you have an absolute value, you can always rewrite it as a piecewise function. We had to do that before when it comes to absolute values in integrals because I couldn't do that by hand. I had to separate it. Okay, on a calculator, the calculator would totally do that and loves doing that. But by hand, we would have to separate it. For derivatives, to take a derivative of an absolute value, you have to split it. And you can see here, the derivative of negative x is the negative 1 we wanted, and the derivative of x is the positive 1 we wanted. So it totally kind of worked out there. Now, why is this a problem, you could say? Because let's do the same thing over here. What if I ask you for what is the distance of y is equal to absolute value of x between negative 1 and 1, okay? Here is my problem. To find our distance of shit here, we would have to say, let's try it. Let's go ahead and plug it in. We're stuck with square root of 1 plus, what is the derivative? What's y prime? And what's the y prime of absolute value of x? Don't know. I don't know. Okay, you guys all see where we stalled out, where we died? We're asked to take the derivative of y, but we don't know how to take the derivative of y. So we have to break it. And we break it by saying, hey, you know what? We don't know what the derivative of y is, but let's rewrite it. Y is equal to absolute value of x, right? And let's rewrite it as a piecewise function real quick. When x is less than 0, we have to say it's negative x, because that would make it to a positive. If x was greater than 0, we can be totally cool with this. All right, let's take the derivative. Y prime is negative 1 when x is less than 0, and positive 1 when x is greater than 0. Okay, cool. So we have to take this problem and we have to split it. Between negative 1 and 0, see, that's the left side. That's the left side here. That's my left side of the equation. We say square root of 1 plus, what's the derivative? Negative 1 squared dx. Because that's the left side of the problem. What's the right side of the problem? Well, we have to go all the way up to 1, right? All the way up to 1. And let's look at the right side of the problem. I'll use this as a different shading here. Right here, that's the right side of the problem. So much thinking involved, Mr. Ko. You're right. It's not impossible, but it does take a lot of work. So here's our issue. If we end up with problems that have an absolute value in it, we have to split it. So we have to rewrite the problem so there's no absolute value, because we can't take the derivative of that stupid absolute value problem.